Hi everyone. So today I'm going to be going over how to simulate flow across a flat plate and some of the data you can pull from it. So traditionally I would start from it built from nothing and show you how to build it, but to save a little bit of time, I have my flat plate pre-set up and I actually just found this cool zoom feature. So I'm going to show you that real quick. So for most of the time, you're going to want to model this in a wind tunnel, but for this experiment, we were just told to put it into a container. So to avoid any blockage effects and to allow my flow to fully develop, I have my flat plate right here. It's 0.1 inches thick by 6 inches in length, and it's nicely nestled in this 12 or 24 by 24 inch just container pretty much. I fixed the surface. So this is what our fluid flow is going to be, all this red stuff here. And so from here, I'm going to move over to our modeler. Again, I do have this pre-set up, but I will walk you through it. It just was taking a long time to mesh while I was doing it on the recording, so I did it separately, but I can walk you through it. So I inserted the mesh method, sizing, and inflation in that order. For the method, I went with an all triangles method, and I can show you the specs I'm using on that as well. Oh, here it is. It's already here. So yeah, it's just changing this to triangles. I just found that that's the best way that works for my system. Using the other methods just kind of give different results. And then the body that's selected is just, of course, where my flow is going to be. For my body sizing, I'm using 0.05 inch sizing, which just makes sure that the mesh is really tight. And then my inflation, I created name sections. I'll show you that in a second as well. And so I did that where this is my main geometry and the scoping method is around the flat plate. I didn't touch the transition ratio, but I gave it 8 maximum layers with a growth rate of 1.001. And then as far as name selections go, we go over here and I want to make sure I'm choosing edges. I'm actually going to create a name section for the top, and for the bottom, right click, create name section. We're going to call these walls. The other name sections that I have our lovely flat plate, our inlet velocity, our outlet pressure, and of course, you just saw me create the walls. One very important thing to note is for your inlet velocity and outlet pressure, they need to have the word inlet and outlet in them, or else when you're in the setup, it will not recognize those as the inlet and the outlet. So we'll go back here on mesh. We shouldn't have made any changes to our mesh, which is why there's no box here, but if there were some sort of box here that says your mesh is out of date, you'd want to regenerate it. I'm just going to push the update, which pushes it back to Fluent. So we got that little pop-up here. We are good to move over into the simulation. So we'll go back to setup. And since it is such a large object, it will take a while to load, especially since I am recording on Zoom. But we'll do double precision with 4 solvers. That usually works well for my machine. That's just pretty much boilerplate pop-ups. You can just get rid of those. And then I am going to move this all the way up top for this part. Thought I was, there we go. We'll put it there. Okay. So we're gonna just kind of go through some stuff. Under models, we come in here, we wanna make sure we have turned our energy on. Under viscous, I'm gonna change it to K epsilon. That's just a solver that I've been using all semester, so I wanna keep that consistent. I don't have to change any of this other information. I want to check the properties of my air. So I see the density, that's important. And then this is also actually really important. This is the kinematic viscosity. So I'm just going to leave all of those as is, close out of this. The solid's aluminum, but that's not something I need to worry about. We're going to boundary conditions. So for this, our absolute velocity needed to be 10 meters per second. I'm not changing any of the other information, not changing the temperature either. So we're all good on that front. Apply one more time to make sure it works. Then we're good to close. And then we're going to go to outlet pressure, just to double check, make sure it's initialized how we want it. So the outlet pressure is 0. That's what we want. We don't want the pressure coming out to be any different than the atmospheric pressure. So we're all good on that front as well. And again, 300 degrees Kelvin, good to go. Apply and close. So the next thing we need to do is initialize, and I'm going to initialize using 100 just to guarantee convergence. You probably don't need to do that high, but I found that that's just something that, guarantees I'm not going to have to redo anything. It does take a bit longer, but again, in my opinion, I do think it's worth it for what we're working for here. Almost there. It's really good to see that this value is getting so low. The lower this is, the better our result's going to be, as this is the scalar. So again, like I said, this just really guarantees good convergence, good values. The more precise you can make something, I know it introduces some other minor errors, but the more precise you can make something in general, the better the result's going to be. All right, so we are all initialized. We're gonna come over. We're gonna run that calculation. Make sure you change your number of iterations. I'm gonna do 250. Again, it is going to take a while, but like I said, it means that it's gonna really get to a good point. You like to, they do a pretty good job of showing you how long each iteration takes. So you can see they're getting faster as they go, but each iteration taking about 2 seconds. I actually think too, this might be the time remaining to complete the iterations. So if you haven't already, I definitely recommend just kind of skipping until um, done with this part. It'll make a lot more sense. Just about halfway there. We're getting there together. Pretty. We are good to keep going. So you finish your calculation, you finish running the simulation. Now you're going to want to start pulling the data. So you're gonna first come down here to graphics. We're gonna go to contours. And we want a contour of the velocity. We're just gonna select all our lovely surfaces here. Compute. And then save display. So then if you were to zoom in, unfortunately, there's our fun zoom feature. Whoop. The biggest thing we definitely need as digital technology users is patience. It'll figure itself out. It's not going to crash. There we go. So I'm also going to turn on these contour lines just because I know that was part of the assignment and I actually just realized that button was there. So save display and we're good to close. We're going to use our lovely zoom tool to zoom in as much as we can while keeping it straight. Zoom out. Again, you can see it's pretty finicky. Um, Not 100% sure why it's rotating. It'll be okay. Um, yeah, this is what it's supposed to do. This really just goes to show as you guys are having trouble with the software, as it's being finicky, as it's struggling to load, as it keeps crashing, as shapes are turning. It's not just you. It's happening to all of us. And it'll be okay. If it does crash, I will go ahead and pull up a different version of the file, um, so that I can continue showing you the results and how to pull what you need to pull. Such a fun time. I'm gonna go ahead and pull up the other version. Um, and just continue with that. So desktop. So I know we are supposed to start from scratch, but since the system is struggling right now a lot more than it should be with the Zoom, I'm just gonna show you from here and I'll continue where I left off in the other one. So I do believe my geometry does look slightly different, but I will just catch up to speed as far as actually running the experiment. That way this video does not take that long. I meshed it using the exact same format. Everything else is exactly the same. And I will rerun everything as well. As soon as it decides to load. Technology is just not on my side today. That's okay. So this is the one I actually used to put the results together for the report. It is longer than it is tall, but so to continue from where I left off, I will reinitialize and rerun the calculation. I'm just gonna speed this up a bit and do 50, and then I'll cut the other one in half as well, to see if that helps it go a little faster. Alrighty, we're gonna come run calculation. I'll change this to 150, calculate. So even though it is operating on less iterations, it shouldn't be an issue as far as data is concerned. It should just be able to do what it needs to do. So it is almost done. Okay, so resuming where we left off, you're gonna come over here. We're gonna make the velocity And then I know it does ask for the velocity zoomed on the flat plate as together with the velocity vectors. So velocity magnitude. I do have other surfaces in here just because I had to rename certain things when creating this file initially, but it really doesn't change anything as far as backend stuff goes. And then we're just going to come zoom in on our flat plate. So this might be a really appropriate time to play around with this as far as the actual chart goes. I don't know why it's not fully loading or if it's going to crash again, but yeah, it's a day. I do want to show you one thing as well. We're gonna do it again with contour lines and see how that affects the display at all. I don't think it's really gonna change it too much as far as actual looks goes. But it does look like it gives everything a really good boundary. So that might be an option to go with if you decide to go with that. To get the vectors, it's really similar. So we're going to call it vel vector. Velvec works. Again, we're just going to do it on everything. Compute, save display. Wait for it to load. So this one definitely looks pretty different. It's just a different look. Again, you can play around with the settings and see if any of it helps. I know sometimes playing around with the vector options can help. Changing the scale head to something bigger. I'll show you what that looks like. So it really just kind of darkens everything. I'm not totally sure why everything's a little grayed out right now, but you can definitely see like the wake left behind. And then if you zoom in real far, you get a really good picture of the way the flow is reconverging after the flat plate. So the next thing that you need to find are the variation of the local skin friction with respect to the Reynolds number. So unfortunately, there isn't a way to do that in here. So you're definitely going to want to export to Excel or another data processor like that. So to get the skin friction coefficient along the flat plate, it's just like that. I know sometimes we had some issues with it, so you might have to create a new surface. I believe that is what you have to do, a new line. And we'll just call this top plates. And then it's in meters. Let's just go back and change that real quick because obviously everything's in inches. We want our length to be in inches. Close. Come back into here. New surface, line. Top plate. Now you have to remember where you did the top of the plate. So I know for me, it runs from 0 to 6 in the X and from 0.1 to 0.1 in the Y. So I've had that issue. The way I worked around it is if you just add a few zeros. It's not exactly on the top surface, but it is small enough that it should be in the boundary layer. And it looks to be this line 3. I don't know why I didn't save it as top plate. That's okay. We'll save plot that to show you what that looks like. And so that's our skin friction. And then you're going to want to pull that to a file. So you would write it and save it. I actually did static pressure for some reason instead of the skin friction. So I'm checking that. This is our skin friction coefficient. And then you would do the same thing, same surface, get the local velocity, say plot, export both of those. And then let me check real quick what else we need. You need to plot the laminar boundary layers. So the best way to do that is same thing. Oh, get the dry coefficient as well. Dry coefficient is under report. Forces. Is it there? I always lose it when I need it. I'm so sorry. Give me 1 second to find it. I never remember where it goes. I'm pretty sure it's in here though. I do apologize for that. But I know there is a way to pull the drag force. It always just takes me a second to find it. Thought it was under forces. We'll give that another shot. Cancel, print. Yeah, that's what it is. So if you go to forces on your top surface, which is just my flat plate, this is the total drag force that you want. And then the last thing is just you need to plot the laminar boundary layer velocity profiles at 2 different points. So the best way to do that is to pull the velocity in an XY plot. You're going to want to create a new surface, a new line. For the top, it's going to be at x equals 3 inches, x equals 3 inches, 0.1001. You can also do it on the bottom since they're symmetrical. And do it that way as well, but we'll just do it this way for now. On line 8, you're going to pull the velocity and you're actually going to switch, put the position that way, velocity, and then line 8. We'll just switch it back. This is one of those tricky things where sometimes things are great. Sometimes they are not great. Let's just create a new surface. I'm gonna just do it on the underside. Airfoils are symmetric, or flat plates are symmetric, I should say. So we'll do from 3 inches to 3 inches. Oh, that's why. Goodness. 1.001 and then make it something really long, like 12 inches. That should be this line. Sometimes things go well, sometimes they don't, and that's okay. So this is the curve length with respect to the velocity magnitude in meters per second. So you would write this to the file, get that data, and then you need to find u local over u infinity and then y over delta and plot those and the theoretical variations. And that is a very long and lengthy summary of how to do the flat plate analysis for this project.